What specific problem does the new method or algorithm aim to solve?
The new method or algorithm aims to solve the problem of transcending expert sources in generative models. Specifically, it addresses the issue of generative models trained on expert data outperforming the best individual experts. The method focuses on achieving transcendence by denoising expert biases and consolidating diverse knowledge through low-temperature sampling. This approach allows the generative models to surpass the performance of the human players who produced the training data, showcasing the capacity of the models to outperform individual experts in specific domains, such as chess. The algorithm aims to formalize the notion of transcendence and provide a theoretical framework for understanding and enabling this phenomenon in generative models.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method works by training generative models on expert data and utilizing low-temperature sampling to achieve transcendence, where the model outperforms individual experts. Here is a step-by-step illustration of how the algorithm works based on the provided text. 1. Training on expert data. The generative models are trained on expert data, such as human chess transcripts, where the models predict the next move in the game autoregressively. 2. Low-temperature sampling. The key to achieving transcendence is through low-temperature sampling. By applying a temperature sampling scheme to the learned function, the model generates distributions that skew towards better moves in specific game states. 3. Improving expected reward. Lowering the temperature through sampling shifts the expected reward distribution towards better moves, especially in critical game states where errors are likely to occur. 4. Denoising expert biases. Low-temperature sampling denoises expert biases by consolidating diverse knowledge and majority voting, leading to improved performance over individual experts. 5. Dataset diversity. Dataset diversity is essential for transcendence. Models trained on diverse datasets are more likely to transcend and outperform individual experts compared to models trained on less diverse datasets. 6. Validation through chess models. The algorithm's effectiveness is validated empirically by training chess models that surpass the performance of the players who generated the training data under low-temperature sampling. 7. Quantifying dataset diversity. Dataset diversity is quantified through normalized entropy on the action distribution, providing insights into the diversity of the dataset and its impact on model performance. 8. Achieving transcendence. By combining training on expert data, low-temperature sampling, and dataset diversity, the algorithm enables generative models to transcend and outperform individual experts in specific domains like chess. 9. Future research directions. The algorithm lays the foundation for future research to explore transcendence in various domains beyond chess, and to understand the broader implications and practical implementations of leveraging generative models to exceed human expertise. 10. Ethical considerations. The algorithm also raises ethical considerations in the deployment of generative models and emphasizes the importance of understanding the limitations and implications of achieving transcendence in AI systems.
What are the theoretical or practical benefits of using this method?
The theoretical benefit of using the method described in the paper is the concept of transcendence, where generative models trained on expert data can outperform the best individual experts. This method leverages low-temperature sampling to denoise expert biases and consolidate diverse knowledge, enabling the model to achieve transcendence by improving performance over the experts that generated the training data. The practical benefit of this method is demonstrated through empirical validation in the context of training chess models. By implementing low-temperature sampling, the models were able to surpass the performance of the players who provided the training data, showcasing the practical effectiveness of this approach in improving model performance. Overall, the method offers a systematic way to enhance generative models by surpassing the capabilities of individual experts, leading to improved performance and potentially pushing the boundaries of what generative models can achieve in various applications.
How is the method validated or tested?
The method is validated or tested by training several chess models on a dataset of human chess games from Lichess.org, with approximately 1 billion games from January 2023 to October 2023. The models are trained on the next token prediction objective, where the only input they see are the moves and the outcome of the game, without any rating or reward information during training. The dataset is truncated by a maximum rating to limit the model's exposure to data up to a specific rating. The models are then evaluated by playing against a popular open-source chess engine at different levels with a 100 milliseconds timeout directly on Lichess's platform. The GLICKO2 ratings of the models are calculated based on their performance against the chess engine. The evaluation is conducted by playing a certain number of games against different levels of the chess engine and calculating the GLICKO2 rating and rating deviation of the models. This process is repeated for each model and level of the chess engine to obtain calibrated ratings for the models. The results are reported with confidence intervals to assess the performance of the models. This experimental setup and evaluation process validate the method by demonstrating the model's ability to transcend their expert sources by outperforming the players who generated the training data, particularly under low-temperature sampling conditions.
What results were achieved with this new method?
The new method achieved transcendence in generative models, specifically in the context of chess modeling. The ChessFormer 1000 and ChessFormer 1300 models were able to surpass the maximum rating seen in the dataset, demonstrating significant levels of transcendence by outperforming the human players who generated the training data. This transcendence was enabled by low-temperature sampling, which denoised expert biases and consolidated diverse knowledge, leading to improved performance over individual experts. The models achieved transcendence by performing better on specific key game states, where low-temperature sampling skewed the expected reward distribution towards better moves, resulting in a relatively large improvement in reward for certain game states. Additionally, the necessity of dataset diversity for transcendence was highlighted, emphasizing the importance of varied expert perspectives in enabling models to transcend expert sources. Overall, the results showed that low-temperature sampling can induce transcendence in generative models, allowing them to outperform their expert sources in specific domains like chess modeling.
What are the limitations or drawbacks of the method?
The limitations of the method outlined in the paper include the assumption that game conditions at test time match those seen during training, which may not hold in scenarios involving composition or reasoning. Additionally, the paper acknowledges the need for future research to explore transcendence and its causes in domains beyond chess to assess the generalizability of the findings. Furthermore, the method relies on dataset diversity for enabling transcendence, indicating that models may struggle to transcend if the dataset lacks significant diversity. The paper also mentions the potential ethical considerations in the deployment of generative models that achieve transcendence, suggesting a need for further exploration in this area. Lastly, the method does not provide evidence that low-temperature sampling leads to novel abstract reasoning, but rather focuses on denoising errors, indicating a limitation in terms of producing entirely novel solutions beyond human expertise.
What future work do the authors suggest?
The authors suggest several avenues for future work in their paper. They propose investigating transcendence and its causes in domains beyond chess, such as natural language processing, computer vision, and text-to-video, to assess the generalizability of their findings. Additionally, they mention the need to explore practical implementations of transcendence and ethical considerations in the context of deployed generative models. Furthermore, they highlight the importance of extending their theoretical framework to cases involving composition or reasoning, where game conditions at test time may differ from those seen during training. Overall, the authors emphasize the potential for leveraging generative models to surpass human expertise in various applications, pushing the theoretical boundaries of what these models can achieve.